Hello everyone, my name is Logan Nelms, and in this presentation I'll be discussing carbon nanotubes. So what are carbon nanotubes? Carbon nanotubes, or CNTs, are a unique form of nanotechnology with practically an unlimited number of capabilities and applications, with more being discovered just about each and every day. So essentially CNTs are comprised of one or more layers of graphene in a flexible and cylindrical hexagonal shape. Think of it almost as a fancy straw-like structure, and they're shaped in this way because of their influence from van der Waals forces. So what makes CNTs unique? Well, CNTs, the nanotubes themselves, are the hollow-like structures which you're probably thinking of. Um, However, these tubes actually make up a material that is one-dimensional. So what that means is that CNTs are one-dimensional and they only exist in the x direction, which is hard for us to understand considering that we don't really ever deal with anything one-dimensional. Um, Daily life, most of the time we only deal with two-dimensional or three-dimensional. Um, but believe it or not, there's actually some things that are that exist in that one-dimensional uh, material phase, and carbon nanotubes are one of those. So this is what carbon nanotubes typically look like. So start out with a sheet of graphene in the top left corner, and if you were to just roll that up like a piece of paper, then you would get a single-walled carbon nanotube. And so it's in the shape of a cylinder, and it also has the smaller circles, which are not really circles, they're actually those hexagon shapes, which which I described earlier. But if you were to roll up single-walled nanotubes within one of another, then you would get the multi-walled carbon nanotubes, which is on the bottom right side, which is essentially just a bunch of single-walled carbon nanotubes. Or you could take multiple layers of graphite and just roll them up to also get the multi-walled carbon nanotubes. So talking about the types of nanotubes, um, from the previous image, you may have been thinking that there was only one type of CNT. However, there's actually three types, and the previous image showed the single-walled carbon nanotubes and the multi-walled, or the double-walled, but there's also the multi-walled carbon nanotubes, which I'll discuss in the upcoming slides. But the main difference between the types is, of course, the number of walls or layers that each one acquires. So, not hard to understand why there's this type, and this type. Just the number of walls that they have. So, single-walled carbon nanotubes are made when the single sheet of graphene is rolled into that cylinder shape, which I previously mentioned. And the double-walled nanotubes consist of two walls or layers in the same shape. Yet again, you could get those by the multiple sheets of graphite and rolling those up to get the double-walled, or you could basically just have so many single-walled nanotubes, just one inside of the other. So, like I said, just think of it as rolling a piece of paper and basically placing one inside of the other. So multi-walled carbon nanotubes are a little different when compared to the single and double-walled nanotubes. The multi-walled nanotubes are essentially just ring after ring after ring after ring of nanotubes within one singular nanotube. So if you think of it, one of the sources I read described it as being like a tree trunk when you cut them open and you see all the rings within the tree. Well, that's essentially what a multi-walled carbon nanotube is like. They do have a larger surface area, however, they are less flexible and they can also experience some structural issues just basically because of the amount of layers that they have. So yet again, they do have some good qualities, but with that also comes some some issues. So here's a image of the types of production for CNTs. So you have three main groups. You have the physical processes, the chemical processes, and the miscellaneous processes. And I will further dive into these methods and processes in the upcoming slides. But here's just a quick overview of the different methods used. So here we have the two different types for the physical production methods. So you have the arc discharge method, or ADM, and then you have the laser ablation method, which is LAM. So for the arc discharge method, current is transmitted via an arcing process through typically what is a helium-filled room, and the room is heated to a high temperature, normally above 3,000 degrees Fahrenheit. The room also contains graphene, carbon, and metallic particles which aid in the creation of the actual nanotubes. And once that arc goes through that material, eventually a soot remains, and that's what actually contains the nanotubes. And then for the laser ablation method, you have a quartz tube filled with pure graphite, and then that is then heated within a chamber, normally to above 2,000 degrees Fahrenheit, and a laser is used to essentially vaporize the graphite material within the quartz. And through that vaporization process, you get carbon nanotubes through almost a soot-like leftover type situation. So here we have the chemical production methods for creating CNTs. So you have the CVD method, which is the chemical vapors deposition method. You have the what I call HIPCO method, or the high pressure carbon monoxide method. And then you have the COMO-CAT method, which is basically just cobalt and molybdenum cat, which is essentially just using the elements of cobalt and molybdenum with graphite powder to create CNTs. And all of these essentially are just adding chemicals in a heated or pressurized environment, adding along with graphite powder to create CNTs. And here's just a image of the CVD method. So over on the left you have your chemicals that you would be adding to your graphite metallic elements and whatnot, and that would be in the catalyst box, and that is within the furnace, which would then be pressurized, heated, whatever, and would essentially turn into carbon nanotubes. So like I said, there's many properties of CNTs, and these are just some of the main properties. So you have heat conduction, you have metallic / semiconducting electronic properties, you have the length to diameter ratio, which is greater than 1,000,000 to 1, which is unlike practically any other material. You also have the high ductility, you have thermoelectric, you have electromechanical properties, as well as optical applications, and many more. So the unique structure and shape of carbon nanotubes allows for them to be bent and manipulated into many different shapes, which can then be used for a specific purpose. In the medical field, for example, nanotubes are beginning to be used to treat types of illness by transporting drugs throughout their structure. And since they can be manipulated, bent, whatnot, they can directly medicate where they are intended to. Since they also have a high tensile strength and ductility, they can be manipulated without the fear of breaking. And if needed, CNTs can be wrapped or lined with carbon fibers to further enhance their structural capabilities. So when we talk about the qualities of good carbon nanotubes, there's not necessarily a set of specifications that say these are what good nanotubes are and these are what good nanotubes are not. But more it's based on what kind of job you need the nanotubes to perform and how well or how capable they are of performing those tasks. So, for example, if CNTs were going to be used in a medical field, one would want qualities such as cell penetrating, drug loading capacity, as well as high solubility, just so that they could perform that job. So essentially, it's job based. So not really, this is a good nanotube, this is a bad nanotube. It's also good to remember that the length to diameter ratio is also a quality that some may want in a nanotube to consider it a good carbon nanotube. But yet again, it's more just job-based performance. So it's also to remember that they can be wrapped in polymers or surfactants that can create the better structural integrity, higher solubility, or lower toxicity of CNTs. So yet again, you can add things typically to the nanotubes to just further enhance their capabilities to perform that job that they're needed for. So now we'll discuss the actual applications of CNTs. So yet again, if you haven't noticed already, I've already mentioned some applications of CNTs, but they have practically a limitless amount of applications. But common applications of CNTs include biomedical, electronic, mechanical, thermal, structural, optical, and just many other applications revolving around engineering and science. And over the next few slides, I'll just get into some of those applications. So typically, carbon nanotubes are seen in production of many different products. Some of these products are within the textile production, where nanotubes are used in building the actual structural integrity of fabrics, which can make them stronger or more lightweight, just depending on what is needed. When voltage is applied to CNTs, they're also capable of producing 100 times the conductivity of silicon, which can make them a very useful tool in circuit work. So I was really surprised to figure out just how conductive carbon nanotubes were, but it is really remarkable that they are capable of producing that much conductivity, and they are as small as they actually are, since they're basically nano size. So another application of carbon nanotubes is their applications within the medical field, and they're really good at targeted drug release. So they can directly release drugs into a specific area or even specific cells. So that's why they are great candidates for cancer treatment. So typically, cancer infects some or most of the cells within a certain area. However, traditional treatments such as chemotherapy can destroy sick and healthy cells, which can lower the immunity of the patient and leave them at a even greater risk for developing another illness. But with CNTs, you could actually use the CNTs to target just sick cells, and that would greatly increase the success rates of cancer treatments. So hopefully, now that this presentation is over, you have a better understanding of what carbon nanotubes are and how they are applied and how they are extremely useful in not only industrial settings but many others as well. And I believe that there's many new capabilities that will come out in the future for these structures, and I just encourage you to to research them yourself and see just all the useful applications that they have. And here's a list of my sources. Thank you.